So this video is about part 5 of the learning unit 6, which is on the crystal field theory. So what is crystal field theory? So crystal field theory is a theory that considers the electrostatic interaction between the lone pair electron in the ligand and the electrons in the metal ion. So normally crystal field theory is abbreviated as CFT. And as far as the S and P orbital are concerned, so these orbitals, they are symmetrical and cause no energy splitting. However, when the orbital involved, it will interact selectively and it will cause some energy splitting. So in order to understand CFT, one has to know the description of the lobes. So you do know that the orbital has 5 types of suborbital. So these 5 suborbital has different description. So the first suborbital here is the dxy, number 1. So it has 4 lobes. 4 lobes lies in between x and the y axis, like what we have shown here in figure 1. And then the second one is dyz. So dyz has 4 lobes, lies in between y and the z axis. And the third one is dxz, which has 4 lobes, lies in between the x and z axis. Okay, so these three orbitals, their lobes lie in between the axis. In between, yeah, in between. This is the keyword. Okay, for another suborbital, which is dx square minus y square, the 4 lobes lies on the x and the y axis. It lies on the axis. Here, you see, the lobes intersect the axis. Okay, so for number 5, suborbital number 5, which is dz square, you can see that this is an odd-shaped suborbital. So you have 2 lobes on the z-axis, 2 lobes here on the z-axis, and the donut-shaped ring that lies on the xy plane around the other 2 lobes. So there is donut in the middle. Okay, once you know the description of the lobes or the suborbital, you will know how to draw the orbital splitting diagram when encounter coordination complexes. Okay, as you already know, complexes can have different types of geometry. So in this part, we are focusing on 3 different geometries, which is the octahedral, tetrahedral, and also square planar. So let me brief you on the octahedral complexes. So in octahedral complexes, the repulsive interaction between metal and ligand electron will be greatest for electron in orbital which have their lobes directed along the Cartesian axis, meaning along the Cartesian axis, when you have ligands come in, so the energy will increase because there is repulsive interaction. You know that metal has electron, ligand also has electron, but when they meet up, they tend to repel. That is what we mean as repulsive interaction. So in this case, ligand will come at the axis. Okay, so octahedral shape look like this. This is x-axis, z-axis, and y-axis. So octahedral complex is actually formed in a cube. So ligands are on the center of the cube face. Okay, this is cube. So this is its face. Okay, and the ligands are on the center of the cube face, meaning the ligand comes directed to the along the axis. So in this case, if you look at the suborbital shape, in the d orbital case here, dx square y square and dz square are the two orbitals that have their lobes directed along the Cartesian axis and they split into higher energy level. Because they have their lobes directed to the along the axis, so ligand will come at the axis here. Okay, so ligand for octahedral, ligand come through the axis. So since the orbital of the metal is located at the axis, so these two suborbital will experience higher energy level. So the d orbital splitting diagram for octahedral complexes is like this, yeah. So you have the lower energy level is dxy, dyz, and dxz, while the higher energy level is for dx square minus y square and dz square. So they will be differentiated by this energy difference. Yeah. So delta means energy difference between these two suborbitals. Okay. Next, let's move on to tetrahedral complexes. For tetrahedral complexes, the energy splitting is in the reverse order to the octahedral complexes. Why it is in reverse order? Because in tetrahedral complexes like this, you notice that the yellow thing here is the ligand, yeah? Okay, so tetrahedral complex in a cube, it looks like this. Ligands are at the corner of the cube. For octahedral just now, the ligand is at the center of the cube. But tetrahedral complex, the ligands are at the corner of the cube, meaning the ligands come in between the axis, yeah. So the repulsive interaction between metal and ligand electron will be greatest for the electron in orbital which have their lobes directed in between the Cartesian axis. Okay, so in the orbital case, so the other three orbitals have their lobes directed in between the Cartesian axis, which then split into higher energy level. Okay, when we look at dxy, dyz, and dxz, their lobes is in between the Cartesian axis. So when we draw the d orbital splitting diagram for tetrahedral complexes, it is in reverse to what we have drawn for octahedral complexes. So in this case, dx square minus y square and dz square has lower energy level compared to the dxy, dyz, and dxz. Okay. Next, we move on to the square planar complexes. Okay, square planar coordination can be imagined to result when two ligands on the z-axis of an octahedral are removed from the complex, leaving only the ligands in xy plane. So as the Z ligand move away, the ligands in the square plane move a little closer to the metal. Okay, this is the diagram of an octahedral or structure of an octahedral complex. Okay, you see this is the Z axis. So in square planar, the ligand 1 and ligand 2 at the Z axis is being removed from the complex, leaving you with a square planar geometry complexes. Okay, in this case, if you can see that if you remove the ligand from the z-axis, meaning the z-axis has no repulsion energy because there is no ligand coming out at the z-axis. So when the ligand move away along the z-axis, so d orbitals with a z component will fall in energy. So for example, the dz square orbital, it falls the most as its electrons are concentrated in the lobes along the z-axis. Okay, and then The dxz and dyz orbital also drop in energy, but not as much because they still have x and y. Okay, and then in contrast, dx square minus y square and the dxy increase in energy because these two suborbital does not connected to the z-axis. Okay, let's take a look at the original octahedral coordination. So this is octahedral coordination. So when it becomes square planar, okay, so the dxz yz from this suborbital has go to lower energy level, and then this dz square here fall into lower energy level, and then the dxy from the octahedral coordination go up than these two because it does not have any z-axis, and then the dx square minus y square will go up. So this is how a square planar d orbital splitting will look like. In the previous slide, I've shown you the d-splitting diagrams for different geometries. But how do we know how to arrange the electrons? So this slide illustrates the spectrochemical series of common ligands in complexes. If you look at the spectrochemical series, you know that at this side, it is a weaker field ligand, meaning it is a weak ligand. So if you have this splitting diagram, I mean the difference between the higher energy level and the lower energy level has smaller delta, meaning smaller difference in energy. And then these ligands always show longer wavelength compared to the right side ligand. Then if you look at the right side ligand here, these are stronger field ligands, meaning they are strong ligands, which when we draw the d-splitting diagram, the delta energy is very large. And then this compound here usually show shorter wavelength. Okay, let's take a look on the effect of the ligand and the splitting energy. Okay, the first example here, if you have hexaaqua chromium 2 iron. Okay, this is your complexes where you have 6 water molecules serve as your ligand. So if we look at the electrochemical series, so H2O is considered as a weak field ligand. So when it is weak field ligand, this chromium is a d4 electron because it is chromium 2 plus. So if it is chromium 2 plus, the d electron is 4. So it is d4 electron. So how do we fill in? Is 4 electron needs to be filled in. Everything singly before they are being paired up. This is because the delta energy is low. So 1, 2, 3, and 4. Okay, this is for weak field ligand. Okay, let's say we have strong field ligand. Strong field ligand like cyanoligand here. Cyano. In this case, the delta energy here, the difference in energy between the C2G and EG is very high. When it is very high, so the electron will be arranged like this: 1, 2, 3, and back again here 4. Before it can go up. This is for strong field ligand. And now, what does it mean by high spin and low spin complexes? Okay. For example, this is a free manganese 2 plus ion without the ligand, so it is D5. Okay, so because it is D5 and it is not paired to any ligand, so the d orbital is not splitting. So it is one line like this, 1, 2, 3, 4, 5. And then when you react it with a fixed ligand, for example the H2O, when you construct, you know that this one has 6 H2O, meaning the coordination number is 6. And usually, when coordination number is 6, the geometry is octahedral. When it is octahedral, the splitting diagram will look like this. And since you have 5 electrons at the orbital, so and this energy level difference is very small. So this is how you fill it. 1, 2, 3, 4, 5. This complex is considered as high spin complexes. High spin complexes meaning you will find more lone pair spin or lone pair electrons in the d orbital splitting diagram. Okay, the next example is when you have a strong field ligand. So strong field ligand, it is normally called as low spin complexes. Okay. When you have low spin complexes, you know that the delta energy here, the difference in energy is very large. So what happens when you have 5 electrons at the d orbital, it will be arranged like this: 1, 2, 3, 4, and 5. So this is how you fill in electrons for strong field ligand. This is the summary of orbital occupancy for high and low spin complexes of D4 to D7 metal ion. Normally, if you have D1 to D3, it doesn't give you any difference because uh, the three electron will always fill in down here, but not up. Okay, so in this case, if you have a high spin with field ligand like this, if it is D4, so it will go up before it pair. For D5 also it will go up before it pair. For D6 it will go up first, only then the 6th electron will come here. This is electron number 6. Okay, for D7 all electron will be filled up until the 6th electron is here, and this is the 7th electron. Okay, for low spin complexes, strong field ligand, the 4th ligand will be paired up with the 4th electron will be paired up with the 1st electron here. And then for D5, it is the same thing. So this is electron number 4, then this is electron number 5. Okay, for D6, this is electron number 4, number 5, and number 6. Okay, for D7 metal, this is electron number 4, electron number 5, electron number 6, and electron number 7. So this is how we fill the electron head using d orbital splitting diagram for octahedral complex depending on the types of ligand. Okay, so this slide is the end of our learning unit 6 part 5, which means we have finished going through all the learning unit 6. Thank you.